we found that XeCl4, let's see, that was, I want to say square planar, nonpolar because the polar bonds canceled out. TeF4 is seesaw shaped. That is polar because the polar bonds don't cancel out. And SeO3 is nonpolar because the polar bonds cancel out. It's appropriate to do a couple more. Number one, to bring it back, because intermolecular attractions require us to know when polar bonds cancel and don't. But the whole idea of polar bonds in a molecule and when they cancel out is important, and we should know about it. So let's take a look at a couple more. Try this one. This is a very simple dot structure to make. Would you make the dot structure for this? Are there polar bonds present in CH2Cl2? Yes, because of that thing right there. FON and Cl, Fonkel. That's what you're looking for, whether bonds are polar or not. FON or Cl. So I see the Cl there. I know there's polar bonds. Now the only question is, do they cancel out? No. What's the shape of this molecule? It is tetrahedral, right? We have a C in the middle with, I don't know how they're arranged, maybe H's like that, and then we have Cl's like that. Now keep in mind that I'm drawing it like this because these three are kind of making a tripod base with the H straight up. And let's see, it would look like, well, like that, I guess. With the H straight up, H to the left, a Cl over here and a Cl over there. Is that a polar molecule? Or do the polar bonds cancel out? Well, the CH bond is nonpolar, so that's nonpolar and that's nonpolar. The CCl bond is polar, so the Cl is more electronegative. That is what it is about the FON and Cl. Those are very electronegative elements. So whatever they're sharing with, they're going to draw the electrons away from those other things they're bonded to. So the electrons are going toward the Cl there and toward the Cl there. Do those bonds, do they cancel out? Are they offsetting? No, they're not. Overall, you would say that over here on the chlorine side of the molecule is electron rich. That's the negative side of the molecule. Over here, behind, like around the carbon, behind where the Cl's are, that side is electron deficient, or electron poor. That would be the positive side. Are you okay with that? So this is a polar molecule because it has polar bonds and they don't cancel out. I would not consider this a symmetrical molecule. You got the two Cl's over there and not over there. You need overall symmetry for it. Like in the case of SeO3, it looked like this. SeO. That's a symmetrical molecule. And since it's planar, the electrons are being pulled all 120 degrees away from each other, making that thing nonpolar. They cancel out there. They don't cancel out there. Any questions about that? Take a look at another. PCl3. Are there polar bonds present in PCl3? Yeah, again, there's Cl. So there are polar bonds. Do they cancel out? Well, to know if they cancel out, you have to know the shape. Got a shape on it? What's the shape? Trigonal pyramid. Yeah, trigonal pyramid. We have the phosphorus in the center, 3 chlorines coming off of it, and they're not coming straight out from it, they're actually being pulled down because the phosphorus also has a lone pair up here, which is repelling these other orbitals away, making it a pyramid shape, not planar. There are polar bonds present. The chlorines are pulling the electrons away from the phosphorus. Are the polar bonds canceling out in this case? No, they're not. If it were planar, they would cancel out because the electrons would be being pulled away and directly away from each other, 120 degrees. But in this case, we would say that the bottom of the molecule down here is electron rich, where the electrons are being pulled down. Underneath here is like where the electron density is. Up in here, it's electron poor. So this is a polar molecule. Are we feeling kind of clear? Okay, one more. Then we'll go on and talk about other intermolecular attractions. IF5. Are there polar bonds present in IF5? We see the F. Yes, there are. Will you do the dot structure of that and determine the shape? You got a shape on that? I think so. It's a square pyramid. So yeah, this one's going to have a dot structure that looks like this. Oh, yeah, none of the I. So it looks like that. We have a coordination number of 6. And when you have a coordination number 6, all the orbitals are coming out 90 degrees from each other in an octahedron. But one of those is a lone pair, so it has to be just removed from it. So an octahedron without one of its bonds makes a square pyramid. There are polar bonds here. In each case, the fluorine is pulling the electrons away from the iodine. Do the polar bonds cancel out, leaving this thing nonpolar? No, it's a polar molecule. Because, now, if it were IF4 in a square pyramid, yeah, they'd cancel out. But the presence of that, so those 4 all cancel out, but this one doesn't have anybody canceling it out. So in general, up above up here is where the electron density is. This part of the molecule is electron rich, it's negative. Down here is electron poor, it's positive. So it's got a positive and negative side to it. Polar molecule. All right. So, I guess I have a few slides on hybridization. I'm going to just skip over them. And we're going to go to this. So we're done here in about 10 minutes. And I think in 10 minutes we can at least be introduced to intermolecular attractions. This is going to cover chapter 10. There are questions in the book out of chapter 8, out of chapter 9, and out of chapter 10. This is going to hit 10. Intermolecular attractions are those attractions between one molecule and the next. What causes molecules to stick to one another? Why is water a liquid? Water is a liquid because the particles are attracted to each other. They stick together. If they didn't, water would be a gas. There are 3 types of intermolecular attraction that we need to know about. Do you remember what they are? Dipole attractions. Yeah, that's why we were talking about this polar business. There's hydrogen bonding. Yeah. There's one other one. London dispersion forces. London dispersion. I missed what you said, Richard.
No, mine. It's like the same thing.
Oh, yeah, Van der Waals. Yeah, same thing. Same thing. In fact, Van der Waals actually covers London dispersion and dipole. Is Van der Waals. It's like an umbrella kind of a thing. The London dispersion forces tend to be weak, especially when molecules are small. As molecules get bigger and heavier, London dispersion forces increase, and then they really matter the bigger the molecules get. So it's kind of, London dispersion force is kind of like gravity, where the bigger molecule is going to have the higher London dispersion force. Like the sun would have more gravity than the Earth because it's heavier. Same kind of idea for London dispersion. What really causes London dispersion, we think, it's a temporary polarity as molecules kind of bounce around. Ben?
This has nothing to do with like fundamental strong weak forces, anything like that?
Strong weak forces, I believe, are strictly confined to the nucleus.
Okay.
I don't think they are.
That sounds good.
My brain is always searching for a simple understanding of strong and weak, but it never gets there. It can't be explained simply, which really annoys me, because my brain needs that. This is a little bit more complex than just saying, well, the heavier the molecule, the more the London force. That is true, but we should know the reason for that. And I'm describing here as electrons bouncing around. Here's what I mean. We know that all molecules, no matter what the physical state, are always in a constant state of motion. Even solid particles, they're wiggling back and forth, they're vibrating. As particles move, whether they're liquid, gas, or solid, the more energy levels of electrons, the more wiggly the electron energy levels are. For instance, if I'm a big, bulky atom, and I'm moving this way, and I bounce into something, my inertia of my energy levels is going to kind of continue moving until the atom bounces back. So the energy levels of electrons, they'll move over this way as they bounce into this thing, and they'll start moving back, and then they'll hit something else, and their energy levels will kind of shift and go this way. Well, that